graph a binomial probability distribution. Our objective here, we want to determine if a binomial probability distribution is bell-shaped, and if so, use the mean, standard deviation, and the empirical rule to check for unusual results. So let's go back a little bit and remind ourselves of a couple of things. First off, the empirical rule, also known as the 68%, 95%, 99.7% rule. If a distribution is bell-shaped, then approximately 95%, we're going to focus on the 95% in this lesson, of the data will lie between two standard deviations of the mean. Mathematically, between mu minus 2 sigma and mu plus 2 sigma. So let's just remind ourselves what that looks like. Here is our bell-shaped distribution. Nothing fancy. I'm not the best drawer, but you get the idea. Right here is the mean. And we go out 1 standard deviation. So this is mean plus 1 standard deviation. We go out 2 standard deviations above. We actually, when we did this, that 99.7 was 3 standard deviations. So I'll go out to 3. And we can subtract and go to 3 standard deviations below. Mu minus 1 standard deviation, mu minus 2 standard deviations, and mu minus 3 standard deviations, or the mean. And we remember that 68% of the data approximately will lie between -1 and +1 standard deviation, 95% between +2 and -2 standard deviations, and 99.7% of the data will lie between +3 and -3 standard deviations. We are focused here. Okay, we're going to be focused in this lesson in from +2 to -2. That's 95% of our data. And I can kind of shade this in. We're focused on this part of the distribution. The 95% that is closest to the mean. Okay? So that's a review of our empirical rule. And in a previous video, we saw how given a binomial with n independent trials and probability of success p, the mean is calculated by n times p. The standard deviation is calculated by the square root of n times p times 1 minus p. So we're going to use both of those two things. So first up, let's use StatCrunch. Let me scroll this, let me move this up a little bit here for you. Let's go to StatCrunch. We're going to go to the binomial graph. And let's take a look at binomial distributions. We want to have the number of trials to be 10, and that's the default in StatCrunch. And we want to look how the graph changes when the probability of success is 0.2 versus 0.5. 0.5, of course, is a tail flip, for example, a coin flip, versus 0.8. Okay, so let's go to StatCrunch. Let me pull StatCrunch for you. I've just opened up a blank StatCrunch sheet. Hope I got it in there. And I'm going to go to Stat, Calculators, and then the word for binomial. And there is the default binomial. As I scroll up a little bit here, we're not going to concern ourselves with the with less than, greater than. We're only concerning ourselves with the shape of the graph. It defaults to 10 trials. It also defaults to 0.5 as the probability of success. Let's change that to our first one of 0.2 and then press compute. All right, notice here. Actually, the graph, in my case, stops at 7. It doesn't go to 8, 9, or 10, but you can see this has a right skew. Okay, the height is over here on the left side, and then 3, 4, 5, 6, 7, and if it kept going, which it doesn't, you can see here it stops at 7, you would see 8, 9, 10, but it very much has a right skew when P, the probability of success, is 0.2. Okay, let's change that to 0.5, which was the default. And then press compute, and there's our graph. Notice right over here, we now have 10 come into play. It shows both 10 and 0. And you can see that this is a bell-shaped curve, a bell-shaped distribution. Okay, approximately bell-shaped. Let's finally change it to a probability of success of 0.8. And we're still looking at n trials. And we'll press compute. And now we have the opposite of what we had at 0.2. We now have a graph where the highest point is off here to the right at 8. 10 is in our graph. And then it has a left skew. Notice again, we don't even see 3, 2, 1, and 0. It's just that little dot right there, kind of right there. But it's going to continue to skew off to the left, and my pad is not even showing that, it's so small. Okay, so we got that. Let us come over to here, and on these guided notes here, you can see that I have simply done a quick, I did actually kind of screenshots of the same things we just saw. This is n trials, and this was when P is equal to 0.2. And we talked about this. You can see this one does go 8, 9, 10. And we said, well, this is skewed to the right. All right, and then we changed the P to be 0.5. And we came up with a bell shape. So these are just pictures of what we just saw. So bell shape. And then finally we went and we did a P, the probability of success being 0.8. And we can see here, the height is over here on the right and it is skewed to the left. Okay, so skewed left. All right, so we kept our number of trials constant, and we changed our P's. We changed our P values from 0.2 to 0.5 to 0.8. Well, here's the question for us. What happens if we increase the number of trials? Let's jot that down. What happens if we increase? 10's not too many, right? 10 trials is really not that many trials. What happens if we increase the number of trials? Okay, let's say we go to 30, for example. What happens if we do that? All right, let's go back to our stat crunch. And I left it with the P being 0.8. Make sure you can all see this. Okay, I left it down here. We had a 0.8. Let's change our N to 30. And press compute. And look what happens. It starts to become more approximately normal. Okay, let's go back and look at that graph with 10 trials again. This one was very definitively left skewed. Doesn't even want to show 3, 2, 1 because those values are so small. A definitive left skew. But when I up my trials to 30, now I see, I get it all, and I start to get a normal, a bell-shaped distribution. Let's increase to 50. And it starts to get more bell-shaped as we work with it, okay? Let's go the other direction. Let's take our probability and change it back to that 0.2, and we'll go back to 10 trials, and we'll compute, and we'll remember that this one had a right skew. Okay, again, we stopped at 7. It goes down, down, down so low, they're not even showing 8, 9, and 10. But as we increase the number of trials, I'll go right to 50 this time and compute. We start to see a bell shape or an approximate bell shape form. So we can conclude here is, as the number of trials increases, the shape of the distribution gets more and more approximately bell-shaped. And as soon as we know something's bell-shaped, we can apply the empirical rule, and that's a rule we can work with. So let's make a note of that. All right, I'm going to turn mine over. Okay, this is an important thing to know, an important thing to keep in mind, and we'll do an example to see how this will work. For a fixed value of p, as the number of trials n in a binomial experiment increases, whatever the value of p is, the probability distribution, the graph, of the random variable x becomes bell-shaped. We just saw that. As we increase the number of trials, it doesn't matter what p is, 0.1, 0.2, it will become bell-shaped. So how do we know? How do we know if it's going to be bell-shaped or not? Well, we have a rule of thumb. And the rule of thumb says if n times p times 1 minus p is greater than or equal to 10, then we can say that the probability distribution will be approximately bell-shaped, and we can therefore use the empirical rule. If we do this math and we get a number that is less than 10, then we say not bell-shaped. We cannot imply the empirical rule because the empirical rule only applies to distributions that are approximately bell-shaped. So this is going to be our standard of when we know whether or not what we're looking at has a bell-shaped distribution. All right, in different words, I guess. Well, taking this into account. Given a bell-shaped distribution, so if we apply, if we come up to here and we apply this and we get an answer that's greater than or equal to 10, okay? The empirical rule allows us to identify unusual observations. Okay? So what's an unusual observation? Well, an unusual observation is defined as something that is outside of that middle 95%. Let's go back to our sketch. Okay, here's our bell-shaped distribution. Here's our mean. If the observation is within 2 standard deviations or above or below, if it's this close to the mean, that's a usual observation. You know, would we define that as not an unusual? So it's a usual observation. It's an expected observation. It's just fine. It's when it's beyond that and the observation is in these far tails that we say, whoa, that's pretty unusual. Okay, you're getting really, really far away from the average. And when you get that far away from the average, you're kind of unusual. For example, if the average height is 5'10", and somebody 6'2" is within the 95th percentile, that person is not unusually tall. But if someone is 7 foot, they're out here beyond the 95%, beyond the second standard deviation, and that person would be unusual, an unusually tall person. Okay, back to here. So our definition for being unusual, right, is you're outside of the middle 95%. You're either way above it or you're way below it. And that's defined as follows. You're above the mean plus 2 standard deviations, or you're below the mean minus 2 standard deviations. In other words, and I've kind of already spoken to this, if the observation is within the middle 95%, that's not unusual. That's expected. If the observation is in the lower 2.5% on this end and way in that little tail, or the upper 2.5% and this little tail on the right, that observation is unusual. Let's do an example. It'll help us. Always helps to have an example. Put my paper over. Okay, according to the CTIA, and we've worked with this example a couple times. 72% of all adult Americans would rather give up chocolate than their cell phones. In a random sample of 300 adult Americans, 230 indicated they would rather give up chocolate than their cell phones. Is this result unusual? Or is this something that makes sense? Well, we first need to know, is this a bell-shaped distribution? That's the only way we can apply the empirical rule. So first off, is this bell-shaped? Okay, that's the question. Well, we know we have a formula to apply if it's bell-shaped. Let's go up to here. Okay, if n times p times 1 minus p is greater than or equal to 10, the probability distribution will be approximately bell-shaped. Okay, so we know that n equals 300. We know that probability of success, which means the person would give up their cell phone, is 0.72. Let's apply n times p times 1 minus p, which is equal to 300, which is n, times 0.72, which is p, times 1 minus 0.72. Put that into our calculator, and out comes 60, which is certainly greater than or equal to 10. 60 is larger than 10. So yes, it is bell-shaped, or it's approximately bell-shaped. Right? We can use empirical rule. We can use empirical, E-M-P-I-R-I-C-A-L. We can use empirical rule to check for, is it usual or not? Is it inside that middle 95% or not? Okay, so in order to use the empirical rule, we need to calculate both mu and both the mean and the standard deviation. So calculate mean and standard deviation. We've actually already done this for this problem, but we'll remind ourselves the mean is n times p, which is equal to 300 times 0.72, which is equal to 216. So the question is 230 close enough to 216 to be considered usual, or is 230 further away from 216 to be considered unusual? That's the question. And we're going to use the standard deviation, sigma, to help us with that. And the calculation for sigma is the square root of n times p times 1 minus p, which is the square root of 300 times 0.72 times 1 minus 0.72. That delightfully goes into a calculator, and out comes 7.8. Okay, let's draw a picture here. It'll help us to make sense of this, and then we'll do the math. So here is our normal, we've said it's bell-shaped. Here's our bell. All right, I'll draw a simple bell here. We know the mean is 216, and we know that if we go up 2 standard deviations, so the mean plus 2 standard deviations is equal to 216 plus 2 times 7.8, which is equal to 231.6. Okay, so this is I'll leave it, I won't even, 231.6. Okay, I'll put it down here. 231.6 is right here. So if our data value is above 231.6, it is unusual. Let's look at our lower value for it being usual or unusual. Down here is 2 standard deviations. This is the mean minus 2 standard deviations, which is the mean, 216 minus 2 times 7.8, which is equal to 200.4. Okay, so our middle 95%, the values that are usual, expected, not unusual, is right here. These measurements, these numbers of Americans, as long as you're close to the mean, close being within plus or minus 2 standard deviations, you're not unusual, or it's not an unusual result. So we're looking for, where does let me get up here. Where does 230 fall? Well, in our picture, 230 falls right about here. Right? Well, that's inside. That's not beyond this point, not beyond 231.6. So 230 would not be an unusual result. An unusual result is above 231.6 adults or below 200.4 adults. So we would say here 230 is between 200.4, which is the mean minus 2 standard deviations, and 231.6, which is the mean plus 2 standard deviations. Okay, it's between those two, comma. So 230 is not an unusual result. Okay, so a lot there. What's, key pieces for, moving us, as you move forward, as N increases, as the number of trials increases, it becomes, let me get up there so you can see it. As the number of trials increases, it becomes bell-shaped or approximately bell-shaped. And when things are bell-shaped, we know the empirical rule. We can talk about that data. We can speak to different possibilities with that data. And the criteria in a binomial for knowing whether or not it's bell-shaped is right here. N times P times 1 minus P must be greater than or equal to 10.